Hi, everybody. We are, 2 days from Christmas break. We can do anything 2 more times. And it's a nice PLC day, so we're getting out early today. Everything's going our direction. I hope your test went well yesterday. But we are going to do the first part of the first lesson of our new notes packet. So hopefully you got that from either Miss Dittis or Mrs. Kohlmeyer. And we are just going to be focused on perpendicular bisectors today. So this whole first lesson is on bisectors of triangles, but we're just going to really worry about what a perpendicular bisector is. So just a few things to talk about before we get into notes. Excuse me, if we just break this apart. Bisector, right, we know that means to cut something in half, and that can look in a variety of ways, right? So if we look right here, there we go. That's an angle bisector, right? That red dashed line's cutting this angle in half. And if we look at this picture over here, we see that this line, CD, is cutting segment AB in half, right? Because of those tick marks. So that would be a perpendicular, or not a perpendicular bisector, just a bisector. On this picture down here on the left, segment AB is cutting in half segment PQ. Again, we know that because of the tick marks telling us PF is the same distance as FQ. And then ending with another angle bisector. So OC is cutting angle AOB in half. Again, we know that because of those congruent markings. So really, again, bisector just means to cut something into two equal pieces. So now we're going to add the word perpendicular in front. And a perpendicular bisector is any segment, line, or plane that perpendicularly intersects a segment at its midpoint. So if we look at our little example over here, I'm hoping you're thinking RS would be our perpendicular bisector because it is going through our segment JK at its midpoint R, right? Because we know that JR is the same distance as RK because of our tick marks. So our example of a perpendicular bisector would be RS. And then I know I kind of covered it up, but it is perpendicular, right? You guys see that little right angle box right there? So that's how we know it's perpendicular. Okay, so with that we have a theorem. We love a theorem in here, don't we? If a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. Okay, one more time. If a point is on the perpendicular bisector of a segment, okay, let's just pause there. So if we look at our picture here, folks, here's our perpendicular bisector. Now they're saying if you're a point anywhere on that yellow perpendicular bisector, then you are equidistant from the endpoints of that segment. That did not work out how I wanted to. So if you're point C on this perpendicular bisector, then you're the same distance away from A as you are from B. That's the big takeaway. And that's what it's saying right here. So line segment C, or geez, I'm so sorry guys. It is early when it's Monday morning. Here we go. So line CD is the perpendicular bisector of AB, which we talked about, right? It has the right angle, and I know that AB is congruent to DB. So then I would know that point C is the same distance away from A and B, or you could write it shorthand, AC is congruent to CB. Now, when in doubt, you guys, in this chapter, if they look congruent or if they look like they're the same measure, they probably are. So that's another way to just kind of go about it. Now the converse, we love the converse, we're flipping the order. This time we're first told if a point is equidistant from the endpoints of a segment, then it's on the perpendicular bisector of our segment. So now this time, folks, we were first told E is equidistant from A and B, meaning AE is the same distance as AB. And if that's the case, then we would know point E is on our perpendicular bisector CE. Perfect. Math and words sometimes don't always get along very well, right? I think sometimes it confuses more than the actual property itself. So let's try this with some numbers, okay? I think it's going to hit home a little bit better. It says find each measure using the perpendicular bisector theorem. So we are looking for AB. I notice that AC is our perpendicular bisector, right? So if AD is 4.1, so is BD, because A is the equidistant from the endpoints of that segment. Now here's the converse, right? I notice that X is both 9 away from Z and W, so that means it's on our perpendicular bisector here. So if YZ is 3, then WY is also 3. Solving for our variable and plugging back in to find RT. So we notice that RS is our perpendicular bisector. And when that's the case, then we would know that R is equidistant from our endpoint. So RQ is equal to RT. Now let's plug in what we know. So if RQ is 2x plus 3, I know that's equal to 4x minus 7. Now we have a nice little linear equation to solve. Get your variables to one side and your numbers to the other. So we're going to have 10 equals 2x. Divide by 2x equals 5. So our x is 5. And now to answer the question, we want to find RT. So if we plug in 4 times 5 minus 7, so 4 times 5 is 20. 20 minus 7 is 13. Perfect. Let's see this one here. All right, we are told that WX is 4A minus 15, and WZ is A plus 12. We notice that that works, or line M, is the perpendicular bisector of XZ. So now we already know that WX is equal to WZ, because again, W has to be equidistant from Z and X. Set up our equation here. 4A minus 15 is equal to A plus 12. Get your variables to one side and your numbers to the other. Divide out and we find that A is 9. Very, very good. Plug back in for WX. So 4 times 9 minus 15. 36 minus 15 gives us a grand total of 21. Woo! Cruising. Very good, folks. All right, now I'm going to hit you with a bunch of vocab probably for the next few minutes here. So the first part is when three or more lines intersect at a common point, the lines are called concurrent lines. The point where the concurrent lines intersect is called the point of concurrency. So if we look at our example here, we notice that lines A, B, and C intersect at point P, right there. So we would say that lines A, B, and C are concurrent lines. Their point of concurrency is point P. So over today and the rest of the week, we're going to talk about different types of concurrent lines. So different kinds of bisectors, different kinds of medians, altitudes, the whole gamut, all right? But today we're just focusing in on what happens when three perpendicular bisectors intersect. And that's what brings us to this picture here. So it says the perpendicular bisectors of the sides of a triangle intersect at a point called the circumcenter. Maybe you want to highlight that on the side of your paper. Maybe you want to highlight it right here. I know it's bolded, but we'll be using these words a lot. So we want to remember that perpendicular bisectors of a triangle intersect at the circumcenter. Okay, a few important things about the circumcenter here. The circumcenter is always equidistant from the vertices of the triangle. So I would star that. So if we look here at our picture, we would know that P, our circumcenter, is the same distance away from A, B, and C. So these guys all in here, I'm going to use, I can't use 3. I got to use 4 apparently. So this segment here, and this segment here are all the exact same length. Okay? List the perpendicular bisectors of our segments. So let's just look at our picture first. So I want to be perpendicular bisectors. So again, we're going to be looking at a lot of different things in triangles this chapter. Like use your context clues, right? Perpendicular bisector. So I know I'm going to need to be making a right angle and I'm cutting a side in half. So I know there's a lot going on in this picture here, but if I look, oh, there's a right angle, so PF, that's one of my perpendicular bisectors. Oh, I see another right angle, so PE. And then I look for my other right angle and I see, oh, PD. So those would be your 3 perpendicular bisectors of our triangle. So let's list those out. And it might be helpful for you to mark up this picture on the left side of your notes. Maybe go grab a marker from the bin if you want, or a highlighter. I think that's all very helpful. Okay, so if we go around here, we did PD, PE, and PF. And it should make sense that you're going through point P, right? Because that's where they're all intersecting. That's the circumcenter, which is our next question here. What is the circumcenter? It's point P. It's point P. Now it wants us to list all the congruent segments, and there's quite a few. So how about let's just start for one tick mark, and we'll go all the way around. So remember, each side of our triangle is getting cut in half, right? So if we look here, our 1 tick marks, that would be AB is congruent to DB. Okay, so this half is congruent to that half, and we'll just work our way around, like I said. Sorry if I'm repeating myself. We'll go over here. Now we're going to 2 tick marks. AF is congruent to FC. Again, that's just another side of our triangle being cut in half by our perpendicular bisector. So we should have 2 equal halves like it says. Let's go purple. And our third side of our triangle, BE is congruent to EC. EE is congruent to EC. So we went around all 3 of our sides that were cut in half. And now the last piece, right, was this little nugget of information right here. The circumcenter is equidistant from those vertices. So remember, those 3 segments would all have to be the same length because they're equidistant. So that would be AP. So now these are my red markings up on my triangle. And then we'd have BP, which is also congruent to, where's our last one, folks? PC, or CP, just to keep it over. Again, a ton of information, kind of like the heart and soul of the lesson is happening on this slide right here. Okay, we're going to finish with one more problem by looking for different measures given that we have the circumcenter of a triangle. Okay, so one more problem for today. So find each measure if Z is the circumcenter of TU. So before we even look at that right side, I think we should go around and maybe fill out everything we can. So remember, if Z is the circumcenter, then the 3 segments coming from Z going to the sides of the triangle would be perpendicular, right? And I'm cutting each side in half. So I'm just going to mark all of my right angles. So those are my 3 perpendicular bisectors. Now folks, let's remember here, I'm cutting each side in half. So if this XU is 19, this half over here is 19. So that's something we know. Another thing we know is if this whole side is 34 VU, and ZY is cutting it in half, then I know VY would be half of 34, so 17. And this half is 17. So that's something we automatically know. And then the last thing we automatically know, you guys, is Z, our circumcenter, is equidistant from the vertices, so the corners of your triangle. So if I look here, BZ is 21, then I would also know that ZU is 21 and TZ is 21. So before we even filled out anything that we needed to over there, this is all free information for us, which is just delightful. Just free. So now let's go back and see what we can figure out. Okay, so TU, I'm going to go from T all the way to U. Easy. 19 plus 19 gives us 38. And maybe you want to put a little nugget of information. 19 times 2 gave us 38. All right, our next one. VY. Well, we already have that right here. We already found that that was 17. 34 divided by 2. 17. UZ. UZ, where is that? UZ. Oh, that's one of our equidistant lengths, right, from the circumcenter to a vertice. It's just 21. 21. WV. Where is WV? Oh, now this is where things get interesting in a good way. We're getting interesting in a good way. So our goal is to find WV right here. Now, unfortunately, I don't know anything about the whole side TV of our triangle. But because you guys are so smart, I'm going to highlight this right triangle here. Just to keep our work nice and orderly, WV. I'm going to label it. I'm going to draw out that triangle. I'm looking for this. This is 21 and this is 15. Based on my conversations with some of you last week, some of you have heard of Pythagorean theorem and some of you haven't. And that's okay if you haven't. We're going to go over it kind of a crash course right now. So in a right triangle, you can find a missing side length if you know two of them by using the Pythagorean theorem, which is a squared plus b squared equals c squared. The biggest thing you need to remember is c is always across from the right angle. So here's your c, and it doesn't matter which one's a or b. It doesn't make a difference. Now once you have this label, we're going to plug it into the Pythagorean theorem here. So I labeled 15 as my a squared, so 15 squared. We don't know what b is, so we're going to call it x squared. And our c squared, our hypotenuse, is 21 squared. And now it just becomes calculator work, you guys. It's nothing crazy. So 15 squared is 225. We still don't know what x squared is. 21 squared is 441. Remember, square just means to multiply by itself. Subtract over 225, we get 216. Now how do you undo something squared? We take the square root. We find that x should be 14.69. So let's just go 14.7. Maybe you want to make an arrow. That was all our work for that guy right there. And don't be lazy at this part. Please get this part out in your notes so you can come back and look at to see how we found that length. Okay, and then our last piece that we need to find here is TV. Easy peasy, right? Look, TV is just the whole thing. So 14.7 times 2. And we get 29.4. Okay, awesome, you guys. Thank you for watching this. Go back to the calendar, click the link for the quizzes. I think it's 12 questions long, and that is what you have for the rest of the class to do. All right, I'll see you tomorrow. Goodbye. Have a great afternoon off. I miss you.